ty będziesz tylko z tablicą.
Ja tylko z tablicą.
Mogę już? So it's our pleasure to welcome our own Michał, and he will speak on nonlinear iterated function systems with overlaps after Boris Solomyak.
Thank you. Okay, yes, I will be talking about a short paper that Boris Solomyak wrote lately. He sent it to several people in January, and now this paper is on archive and is accepted in paper. So, what is the topic? The topic is the iterated function systems. And because this topic did not appear on our seminar for quite some time, so maybe I will remind you some basic information. We will be doing only on the line. This can be done in high dimension, of course. So the iterated function system is simply a finite collection of contracting maps. And if we have the finite collection of contracting maps, then we can find some sufficiently long intervals such that the images of this interval under all those maps lie strictly inside. And this is where the story will happen. Okay, we can apply those maps, and the idea of iterated function system is that we are applying those maps in any order we like, and we are looking where we can go. Yes, so, okay, inside each of those intervals are the first level cylinders. Inside of them we have the second level cylinders, the second iterations of the second images of the initial interval, let's call it somehow, and so on. And there exists unique non-empty invariant compact set. That is the set which satisfies the following equation. It is simply the intersection of this shrinking family of unions of intervals.
Is next affine?
No,
But shrink, uniform.
we assume uniform contraction, but we do not assume that the maps are linear. Okay, why this thing exists is very simple, because we can simply write an example of this set. You can take the symbolic space and we have well-defined map from this space to interval. Defined by this formula. X here is any point on the line, because the maps are contracting and the limit here does not depend on the starting point. So such set satisfies this. You can check that this
projection is continuous, and in fact it is really a projection. That is, you can put the correct metric on the space sigma, and under this map in this metric this map is projection. So this set is compact. Okay, and uniqueness. Uniqueness follows from the fact that when you consider the space of all compact non-empty subsets of the interval with the Hausdorff metric, in this metric, the map F the map defined like this, which is of course going from the non-empty compact subset of I to non-empty compact subset of I, is also contraction, with the contraction coefficient equal to the maximum of the contraction coefficients of the maps Fi. Okay, and if this map is contracting, then it cannot have more than one fixed point.
Existence of a fixed point also follows from shrinking. The set is mapped into itself, and then
the
because
intersection
of
of-
distance shrinks, so the limit must be fixed.
But can you repeat? You said something about projection. I didn't follow.
That is about this map defined by this formula. Okay, what this map is. When we have those cylinders, we can give to each of them the symbolic expansion. So this is F1 of I, so we call this cylinder C1. This interval, it is C11. This should be C12, C1K, and so on. When we the cylinder C omega Ni is always contained in the cylinder C omega N, and the size of those cylinders is going to 0. So for any infinite sequence of symbols, we have the shrinking family of intervals corresponding to the cylinders of the beginning part of the symbolic sequence, and their length goes to 0, so the intersection is just one point, and this one point is exactly this pi of omega. So this map pi, it basically tells us for any symbolic expansion which point has this symbolic expansion.
This I understood, but I saw that. So you just call it the projection. It's not that you are claiming something.
Well, yes, I claim that when you look at this map as the map from one metric space to another, this one metric space is this symbolic space with a properly chosen metric. That is basically the diameter of the cylinder omega n is going, we fix as equal to the diameter of the corresponding interval here. Then this defines the metric on sigma, that is the distance between 2 points is the diameter of the last cylinder they both belong to. Then this map from sigma to I will be contraction. I mean, will be non-expanding. So that's why we call it projection. Well, for the very simple reason, yes, that this distance between 2 points is smaller than the diameter of the last cylinder they belong to, and this diameter is exactly the distance of their symbolic expansions. Okay, so. What we will be assuming about those maps? There are two cases that people consider. One case is when the maps are affine. And another case is when the maps are C1 plus Hilbert. In both cases, okay, there is an important family of potentials defined on the symbolic space. Phi of omega is simply the logarithm of the derivative. This is maybe a bit ugly formula, but what we mean that we are at the point with the symbolic expansion omega 2, omega 3, and so on, and we apply to this the map f omega 1. Okay, so now this behaves nicely when we iterate it. That is when we look at the derivative of the concatenation of maps Fi. This will be the sum of this potential along the trajectory of the left shift map on the symbolic space. Okay, and for this
if people consider not-iterated function system but the inverse, just
yes, and it's
then,
more natural.
Then the function depends on what Solomyak calls conjugate conversion. Depends on backward trajectory, and here on forward.
It's more natural to define this function for the inverse map, which will be simply an expanding map.
Whether more natural.
I mean, okay, it's not so clear that if okay, anyway, we came to this in a moment.
What Solomyak he introduced in scaling function, he considers if we go in your direction, just disjoint intervals.
Yes, we came to
then one
this
defines scaling function, etc. It is the one chapter in my book which reminds you devoted to this Solomyak.
Defining the pressure function.
I assume the sum is over all cylinders of
The
length.
sum is over all cylinders of length n, and S and phi is simply the this thing is phi of omega plus phi of sigma omega plus phi of sigma n minus 1 omega. And omega is any point which we choose from this cylinder. And this thing is well defined. And in order to have this thing well defined, we need to assume the C1 plus delta. that is, this is a bit delicate thing because this header is not calculated in the symbolic space, but it's calculated on the line. But as long as the maps are uniformly contracting, the two things are equivalent. That is, header continuous functions on the real line correspond to header continuous functions in the symbolic space, and vice versa. If we had some map which would be not uniformly contracting, like parabolic fixed point or something like this, this would break down completely. Okay, but in our situation everything works well. We can calculate such pressure. And what it is used for? It is used to find the zero of the pressure function. And if, okay, that there is an important subclass to iterated function system, if the subclass such that we can find not necessarily interval but an open set such that the images of this open set under the map are inside this open set and they are parallel disjoint. If we have such situation, this is called open set condition. Then the outer dimension of the attractor of the limit set is equal to the zero of pressure.
Can you repeat the condition? I mean the definition.
Silly comment, you're missing S in the definition of pressure. Unless I just can't see it, but yeah.
Also, I wanted to ask this projection. Do we know if we look at points where it's one-to-one?
If we have something just a bit stronger than open set condition, that is not only they are disjoint but also the closure at disjoint, then this projection is a bijection, and vice versa. This is if and only if.
But okay, but in the general case, maybe you can say something about the set where it is one-to-one.
Yeah.
Yes. No, difficult. And, okay. This thing here is kind of basic main theorem of the whole theorem. This was done by Sinai Ruel Bowen in the beginning of 80s.
It holds for holomorphic course.
Yes, this all the things I'm talking here about one dimension, but
Complex.
it works in any dimension.
It's important that there is finite number of branches.
Yes,
We
we
need
need
just one.
finite number of branches, we need the map to be contracting, and we need the map to be conformal if you are in higher dimension.
And this is calculable in interesting examples,
Yeah.
finding the zero.
Yes. I mean, it is in general not possible to write this as an analytic function. Yeah? That is, okay, if the map is linear, then what is the zero of the pressure? When this, if we have just linear map with contraction ratios lambda I, then the condition for zero is simply sum of lambda I to power s equals 1. So it's very simple formula. It's not so long. But, well,
Approximate the solution.
yeah, well, you can do anything. Yes, I mean, Mark Policott is doing some with Polina Nova, doing some kind of approximating or calculating from the data things like zero of the pressure. So this can be done, and there are some methods to do it well. Okay. So the open set condition is the situation when we understand everything. And by the way, as you see in the open set condition, we can define the inverse maps. So on each of those sets, we define the inverse map. This will be expanding. The domains are disjoint, so we have well-defined expanding map on some set. We can put anything in between. So we have some interval and well-defined expanding map on this interval. And then you can check that this definition of pressure exactly coincides with the usual definition of pressure for the expanding map on the line. And what goes wrong when we don't have open set condition? Well. First of all, this map here is not bijection anymore. There is some overlap, but there are plenty of points that are grouped together.
When you say open, how do you call it?
Open set condition.
Open set condition. Does this include the closure or not?
No, the open set
is strong.
condition. But if you have open set condition, then it just means that the sets can touch with the boundary. So then we know that there is at most countable set of points where the map is not a bijection. And the countable set from the point of view of dimension theory is irrelevant. So basic open set condition tells us that things are as disjoint as they can be. From the measure point of view, for example, they are disjoint. Okay. In this situation, they are good. And this can lead to drop of the dimension. Because, let's come back to this projection. When we have open set condition, when we have this strong version of open set condition, this version is called strong separation property, this version with closures, then this map pi is in fact not only a projection, it is by Lipschitz. And by Lipschitz map preserves the Hausdorff dimension. So, what we calculate here, the thing that we are calculating here, the zero of this pressure, it's really the Hausdorff dimension of the set sigma. And it doesn't depend on any assumption that open set condition or not. And the set sigma is in the abstract space, and there everything is disjoint.
Is it by Lipschitz?
It is by Lipschitz.
What metric in symbolic space?
This matrix.
Just with this one. It gets a chance.
Okay. But what happens when we have overlaps? Well, the map can have dimension drop and it can have very spectacular dimension drop. Example, if all the maps share the same fixed point, then this invariant, this limit set will be just this fixed point. All the maps will contract this point in whichever order we apply them. And it has dimension 0, and it is totally unrelated to what the maps were. Okay, so in this case we know that the dimension can drop, and the question that we have is, well, whether it happens, how often it happens, what is the dimension after drop, and so on. And this turns out to be difficult. However, one thing that is maybe not so difficult, or at least it was done in the year 2000, is that if we do not have open set condition, then we automatically have the drop of the Hausdorff measure.
Going back to metric, you wrote what are diameters, not what is the metric. So you need to be careful to have triangle inequality if you are not sufficiently careful. But this is purely formal problem. Just want to pay attention, there is an incredible breaks here.
Because, okay, if we have opposite condition, we actually not only know that the Hausdorff dimension equals to the zero of pressure, but we also know that we have positive and finite Hausdorff measure in this dimension. But when we do not have opposite condition, and we automatically know that the measure in this, when S is the zero of pressure, drops to zero. Always. Always.
I have a stupid question. What was the parking measure?
The answer is, okay, here
Here is trivial, yeah.
is the same, but here actually packing measure can stay positive, and there are theorems saying that when we have something called transversality condition, I'm not going to tell you what it is, but when we have one parameter family which behaves nicely, then in such a family for Lebesgue almost every parameter, the packing measure is positive.
It's difficult.
Yes, this is the typical thing. Good. So, where are I? I'm here. Okay, there are here plenty of questions, plenty of answers also. And one question which is what we'll be talking about today is this property of dropping Hausdorff dimension hereditary? In the sense, if we have iterated function system in which we have the dimension drop, and we add one more map, or 5 more maps, do we also have dimension drop in the larger system? This question is completely open in the affine case. In fact, there is a conjecture saying that in the affine case, the only possible reason for the dimension to drop is when some maps completely coincide. There is one
maps or iterates?
in some
Okay, that's okay.
that is when we have some commutation condition in this semi-group generated by the in one direction, of course, if we have some commutation, the dimension drops automatically. That's obvious. But the question is this the only possible situation? And if it was so, then of course it would mean that dimension drop is hereditary in the affine situation.
So when you say that two maps coincide on some level, does it need to be the same level?
No, not necessarily. But if you have some map of level 3 which coincides with some map of level 4, it also means that you have two maps of level 7 that coincide.
Right.
So it's
Okay, change symbol. Notation. No, so they are on the same. Okay. And what about
about the fine situation, and this is the question that was answered by Boris in this paper. He gave very spectacular example showing that it is not hereditary at all. That is, he gave example of the system of free maps such that two of those maps have the common fixed point, but the system of free maps doesn't have dimension drop. So it's the most spectacular situation possible.
Would you say again what dimension drop means?
Dimension drops means that the half dimension of the limit set of the iterated function system is strictly smaller than the zero of the pressure.
And what do you mean by hereditary?
Hereditary, I mean that if you have the system in which you have dimension drop and you add some more maps, then you still get the system which has dimension drop.
So in this example,
It doesn't have.
Okay, by the way, it is clear why something like this is impossible to do for the affine maps. Because for the affine maps, if you have two affine maps which have the common fixed point, then those two maps commute. So there is automatically dimension drop. If we want to find an example like this, we need to look into non-affine situation. And this is bad because the strongest tool that we have in this theorem is such theorem by Hoffman. It is saying if we have what's the name they give? Exponential separation, what condition? Something they call strong exponential separation condition. It says that see, there exists some constant.
Is it bigger than 1? Just something just positive,
Just positive, smaller than 1.
there is n on the right hand side and k on the left hand. Okay.
That is, it says that whenever we take two words of length n and the corresponding maps, this nth iteration of the maps that we started from, those maps are separated at least by something exponential. Something exponentially small, but not smaller than exponentially small.
Is it important here that you have x over lambda and then not x over all segments when you take maximum?
No, this is not important at all. You could take an x on the real line, but then this condition would additionally demand that the maps have the same contraction ratio, but that is not restrictive. So you can take the subset which has subsystem which consists of maps with the same contraction ratio defined in some iteration and apply this condition to this. So yes, you could take x on R.
You mean not x in lambda, but
X in
but then when you continue with the same sequence of vectors, they calculate at most exponent.
yeah, this is
At least exponent.
That is, if we have parameterized family in which this thing is, no, okay. If we have this, then it means that the outer dimension of lambda equals the zero of the pressure. I'm sorry?
So there's no dimension.
So there is no dimension. Okay, and then this is very useful because this condition basically means that under very weak assumption we can say that in some parameterized family this condition is actually satisfied everywhere except the subset of packing dimension 0. Yeah, because we can take smaller and smaller c, and this means that those bad situations are very, very, very rare.
I'm sorry, Michał, can you hear me?
Yes, I can.
So you assume here that the system is so similar, right? This is not for general.
Yes, yes, yes. This is for the affine.
And also you probably need minimum with 1 in the general case.
Yes, I always assume minimum of 1. I haven't wrote this. Yeah, but I need, yes, I should say it. Thank you. Okay, yes, I am completely lying, because the zero of pressure could be larger than 1. And of course, how the dimension cannot be equal to 1. So, cannot be larger than 1. So, the correct way of formulating would be that the dimension is going to be equal to the minimum of 1 and 0 of the pressure. That is, if the 0 of the pressure is below 1, then we have 0 of the pressure, and if 0 of the pressure is larger than 1, then the dimension will be 1.
Wait, so do we say that there is a dimension drop if 0 pressure is, say, 7, and the dimension is 1? Do we say that?
No.
So we don't call this.
No,
okay,
we don't.
so we don't care. So we don't care about the situation when the pressure is zeros to the right of 1.
Yeah, on this talk, I'm always assuming that the 0 is to the left of 1. Yes?
Okay.
But I should.
also a note from Archie, who says that one needs to assume that the generating semicolon is free.
No, this is what the first S is. That is, if the semi-group generator is not free, then this thing automatically falls. That is, indeed, they call something exponential separation condition, which says that something like this happens for all the maps when Fi is different from Fj, but they allow situation that fi can be equal to fj for some watts ij. But here our assumption is that ij are different, implies exponential separation, and this is what they call strong exponential separation condition, and this automatically excludes possibility that the group generated is not free.
Even though you assume it only on a subsequence?
Yes, I think yes. I think yes.
Excuse me, Michał,
Yes?
it's difficult to see, or you write that if the strong exponential separation on a subgroup and there is something in bracket.
On the subsequence ni.
Subsequence. Okay, thank you.
So we do not even need this condition satisfied for every
Yeah,
n.
I know that. Yeah, thank you. Just could not read. Thank you.
I'm sorry. Yes,
It's okay. Thank you.
I can see why it's difficult to read. Okay. So we have such a result for the affine maps, and we would like to use it. The problem is that for affine maps, we simply cannot construct the system like that. No way, no how. But there is one recent result by Boris Solomyak and Yuki, which gives the same kind of result, except not for the subsequent, but the same kind of result that if we have strong exponential separation condition, then we do not have dimension drop. For affine map, for affine iterated function system, non-affine iterated function system, in which all the maps are Möbius transformations. And this thing will be the starting point of the construction. So we construct it. Yes, I want to construct the system of three maps. Two of the maps sharing common fixed point, and the system of three maps having no dimension drop.
Question regarding expansion special condition. Other generalization which says we assume it only on some large subset of pairs ij from sigma.
There were some things like this. I was doing something like this in my PhD. Basically, you can estimate something called correlation dimension of the natural measure, which is the lower bound for the Hauser dimension of the attractor, calculating the number of intersecting paths. That is, you are looking at the singles of given size on some level of the construction, not necessarily the same level, the singles of given size, and you count how many of pairs of intersecting cylinders you have. And if you have this number, you can exactly calculate the correlation dimension of the natural measure. Which means that you have some condition on how strong they can intersect, and still the dimension doesn't drop.
I see.
So this can be used to estimate, say, the size of the parameters in some families of iterated function systems for which we have the dimension drop. Okay. So what I'm going to do now, I can immediately write the example.
T is some constant.
T is some parameter which we will choose.
Okay. And so the answer will be that for some value of parameter?
The answer would be for some value parameter. That is what we will be doing, what Boris is doing in the paper, is that he is proving that this family of maps satisfies the strong exponential separation condition for almost all parameters T. For all parameters except some subset of packing dimension 0, house dimension 0, but for Lebesgue almost every. And then he is going to apply. Okay. How is he going to do this? Well, he has a condition. The condition which is also in the same paper. And condition says that if he has exponential, if he has real analytic family of Möbius maps, it's for a real analytic family of iterated function systems, if we have something he calls.
So let me hold you, let's try and write it a bit larger so that
Yes.
it's visible for my participants.
Yes.
Wow.
Beautiful.
Thank you.
If we have something they call non-degeneracy, then we have this exponential separation satisfied for Lebesgue almost every parameter. What is this non-degeneracy? It means that the projection of different infinite sequences do not coincide. That is, for every omega tau. There exists t, and phi t of omega is different than phi t of tau.
This is, it needs to be for all, almost all.
No, this must be for all. And then, all the charm here is that for the real analytic functions, and either they completely coincide or they are far away except at countable many points. This is the point why real analytic is important here. Okay, so we have nice condition. Now, of course, this condition absolutely cannot be applied to this system. Because for every t, those two maps, they don't depend on t at all, and they have the common fixed point at 0. So any sequence consisting only of 1s and 2s will be projecting to 0 for every t. So this thing is so what Boris is doing, he is, instead of looking at this iterated function system, he is looking at the subsystems. That is, he looks at the subsystem which consists of all the words of length n which contain the symbol 3.
Wait, so n is fixed or is it like a family of subsystems?
We will go with n to infinity.
Okay.
So then he will prove two things. There's one thing, he will prove that those subsystems are actually non-degenerate. Which means that all this machinery that he made in this paper with Takahashi actually shows that there is no dimension drop for the subsystem. That is, the dimension on the subsystem is equal to the 0 of this restricted pressure to the subsystem. One thing, those three maps have the contracting ratios 1/4, which means that the 0 of the pressure is smaller than 1. And so it's okay. Okay, so that's one thing. And the second thing we need is that this, denoted by Sn, the 0 of pressure for this n subsystem, that this actually converges to the 0 of the pressure for the full system. That is, we are effectively, when we are taking longer and longer words here, we are having all the symbolic sequences in which the symbol 3 appears with the positive frequency, and this means that what we drop out is really irrelevant. And so the calculation here is, I guess, not very interesting. And how are we checking this non-degeneration? Again, I will not show you the full proofs, because the full proofs are basically calculations, but I think it will be interesting to see dilemmas. Okay. Weekend notation. If we have an interval A, B, which is strictly to the left of interval CD, then notation is AB smaller than CD. If we have an interval AB such that A is smaller than C and B is smaller than D, then this is denoted as AB smaller or equal to CD. Okay, and then there is also the order on the space of sequences that he introduces, and this is kind of a reverse lexicographical order. As when we have two sequences of length n, then what we are doing is we put those sequences in the reverse order, and then we compare them in the usual lexicographic story. So we have something like, okay, 1n is smaller than 2, 1, and minus 1, smaller than 1, 2, 1, and minus 2, smaller than 2, 2, 1, and minus 2, smaller.
Just to clarify, so for the sequence, when you apply a map, corresponding map, then you start from the right?
The left symbol is the most important, so the left symbol is the map applied last.
Right. Okay.
Okay, so. First level. If UW are two words from two sequences of length n of symbols 1 and 2, no symbol 3, then there exists T such that CU is strictly to the left. Okay, and okay. No, this is not. T is not necessary. Why? Not in this. Somehow managed to mix two lemmas. Those maps do not depend on T, only the third map depends on T. So on those maps, we strictly have the lexicographical order means okay, might be not this. Those two maps have the common fixpoint at 0. So it starts from 0 and then goes further, but one of them is to the left of the other, strictly in this order. Okay, so this implies that C U 3T is smaller or equal than C V 3T.
Right.
Because this means that we start from the map F3, which moves us somewhere to the right, and then we apply to either the map FU or the map FW.
But you start with oh, there's the same T here.
And it also implies that there exists T such that C U3 is strictly smaller than C.
Could you just remind what is C, from where it starts?
What is CT?
Okay,
C.
we have the
Cylinder.
yes, we have the convex hull of the attractor. It starts at 0, goes somewhere to the right. And we apply to this the maps. CU, it will be the map of this interval under the map, the image of this interval under the map FU. And this map can depend on T if we have the symbol free somewhere in the word.
So I assume CT is just to like emphasize that it depends on T.
Yes.
There's nothing else. Still cylinder.
Yeah, my question was rather what was the initial segment from which you
The
started?
smallest one, the convex hull of the attractor. Okay? Why do we have this? Because when we take T large enough, then this map F3 moves us very far to the right, to the very end of the to this interval. And so if we have this, then for T large enough, we are actually strictly to the right. This positive gets shorter and shorter. And the left points aren't really changing, but I mean, this is of course calculation.
Does T depend on N?
This T will depend on N, yes. Depend on U, on V, on N.
Yeah.
But you know, here, that is, formally speaking, this condition was formulated in the paper, assuming that this this real analytic dependence was on the compact interval. But we can apply some kind of change of variables, and we can look at the whole half-line. Yes, the same statement. It doesn't change anything. Okay, so this is one thing. Okay, basically this is the only thing that we need to check, because any word. Okay, no, there is one more thing, because this is about the words of the fixed lengths. So there is one more thing to say. What if the words have not the same length? Now, if we have those two things, then any word you can write as concatenation of words having 1, 2, 2, 1, 1, 2, 2, 1, 3. And then another block which is some number of 1s and 2s, 3. And so on. Okay, so where was this? Okay.
Excuse me, Michał. Excuse me.
Yes?
If you consider the words of, which contains 3, so
Yes.
do you have a kind of transversality restricted to those situations?
speaking, no. That is, we have some range of parameters in which we have, okay, we have some range of parameters in which we have complete disjointness of them, but there might be some other range of parameters where they are intersecting each other, and we do not assume anything about the level of this intersection. They can intersect in the quadratic way.
Thank you. Thank you.
Okay, the second lemma, it is just the calculation. It is if you is the word of length n plus 1, and p is the word of length n. Then Ct u3 is smaller than Ct v3. Okay, here is for every t smaller than 3. This is simply what came from the calculation. That is, for the small t, we have the situation that because the third map moves us very far to the right compared to the first two maps, then if we apply the first two maps, if we replace in one of those, in some place, one of the first two maps by the third map, it automatically moves us to the right.
This is for large t or for small t?
Yeah, this is for t smaller than 3 or larger than 3.
This is for t smaller than 3. That's what he got from calculation.
Huh. It doesn't need to be separated from 0 at all. Because if t is very, very close to 0, I have no idea how this works.
Maybe the segment becomes small.
So I think that that's
Yeah, but this is a strict separation of the cylinders.
yes. And the cylinder with 3 is to the right. Then those cylinders with 1 and 2.
Is it true that when t is small, the cylinders become very small?
Well, the whole interval from which we are starting becomes very small.
Yeah.
So yes, this is true, and this basically means that the maps F1 and F2 became closer and closer to each other.
Okay,
In the limit, you have just the map F1 equal to F2 equal x4, and you have this other map which is x4 plus something, and then you have that kind of.
Yeah.
Yeah, okay, that's the crucial thing. That if t is small, that the interval is small.
Okay. So when we have those two things, I mean, of course, here we have separation for some large t, here we have some separation for the small t, so it's different t for which we have separation for different words, but that's okay because of real analyticity. That is, if we can find one value of t for which the two maps are for sure not coinciding because the corresponding intervals are disjoint, then it means that the set of those t for which those two symbolic sequences collapses must be at most comparable. Because it is real analytic function, everything is real analytic function for every case. Okay, so this is the end of proof. So there is one more added remark in the paper, added remark coming from Balázs Baraň. that it is observation. That is, when we take the natural measure. What is a natural measure? Well, on the symbolic space, we have the S-dimensional Hausdorff measure, and we can project this down. Yes? If we had open set condition, then what we would get would be basically the Hausdorff measure downstairs. If we have overlaps, then we can get something strange. In this case, we have overlaps, but we do not have dimension drop. So we get something. This something is called natural measure. And there is a natural question, what can we say about this measure? Well, in the symbolic space, the measure of every cylinder was, roughly speaking, the diameter of the cylinder to power s. But when we project, then we have exponentially many cylinders of level n around 0. Yes, all those cylinders which are given by words which contain only ones and twos, they are all around 0. So this means that there, the measure of the, when we take some small neighborhood of 0, the measure of this neighborhood is not its diameter to power s, is something like a diameter to some smaller power. It's much larger. That is, in the symbolic space, the local dimension of this Hausdorff measure was s everywhere. But here, downstairs, when we take the projection, we will have a point at which the local dimension of this measure is strictly smaller than s. And this implies that when we look at the LQ spectrum of this measure, then this LQ dimension will be smaller than s for Q large enough. Yes, so this is the remark. This remark is absolutely correct. And Boris refers to some paper of Schmerkin to say this. And this is something I don't understand why, because the relation between the local dimension of the measure and the LQ spectrum, this is Henschel and Procaccia. This is in the 80s, the very beginning of the multifractal formalism. And okay, maybe I don't catch something, maybe, but I think that there isn't anything here, and this thing is indeed long known for many, many decades. Okay, anyway, that's all I wanted to say.
Okay, are there any questions in addition to the question we already had?
I think I was wrong saying that it doesn't matter whether it's max x in lambda or x in the whole interval, because if we change the point, then trajectories approach exponential, and here something must be bigger than exponentially very small, so it has nothing, so the difference if we change x to y is too big, so it has, it says about self-intersecting of the limit set itself, not of points.
No. Here,
so my remark was not.
no. If you take the maximum over x belonging to R, then this maximum is automatically infinite if your two maps do not have exactly equal contraction.
Even though.
So this this simply restricts this condition to only looking at the iterates which have the same contraction ratio.
Okay.
But I think it doesn't make the condition weaker or stronger or anything.
Could you please repeat your remark about Procaccia Henschel?
Okay. The very beginning of multifractal formalism was some papers by Hensel and Procaccio, they are physicists, which were doing something like this. That they had some measures that were coming from the experiments, some distribution of the experimental points, or trajectory of some system which was more concentrated in some area, less in some other area. They called it hot spots, cold spots. Hot spots were the places where the trajectories were spending more time. So, of course, you can take some ergodic measure, and then this simply is talking about the local dimension of the measure. That is, how large is the measure of the ball in different places of the system. For different alpha, you can ask about the points at which the local dimension of the measure is alpha, meaning that the measure of the ball of radius r around this point is, roughly speaking, r to power alpha. And then you can ask how large is this set of such points.
I think for some reason you don't looking at the upper and lower limits at this point because
Yes,
you don't want to model the
yes,
discussion.
for the ergodic
Yeah.
measure, it's not defined everywhere. That's
Yeah,
correct.
of course.
Okay, and another thing is the LQ spectrum. How to write this simply? Maybe I'm making some error of signs or something like this. That is, we divide the space into the epsilon grid, the grid of size epsilon, and then for each square in this grid, we calculate the measure of this set. We take it to power q, take the logarithm and we divide by logarithm of epsilon, and we pass from epsilon to 0. And there is also some normalization constant 1 over 1 minus q. And such an object is called LQ spectrum of the measure.
You need to take some infinable supremum of a different E epsilon.
This is the point that, okay, for non-negative q, you don't have to. Okay, well, first thing, when q equals 1, then this thing is 0 divided by 0. Yeah? Because we divide by 1 over q, and here we are simply summing the measure, and the measure sums up to 1. So the logarithm of this is simply 0. So at q equal 1, we define just the limit with q converging to 1, and again some theorems that when this limit exists.
What's the name of entropy spectrum?
This is called entropy spectrum for q equal 1. And there is the, again, theorem that when q is greater or equal than 0, then this thing is well defined. It does not depend on the choice of the grid. You can translate the grid, you can rotate the grid, I mean, in any dimension. We are in some Euclidean space. When q is smaller than 0, then unfortunately this definition doesn't work exactly for this reason that it depends on the grid, and it can happen that the grid just barely touches the measure, so we have some element of the grid which has very, 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 very small measure, and when we take this very, very, very small measure to the negative power, we are very, very, very unhappy. So then there is some way of improving this, that is, the idea is that we have those elements of the grid, and we have the 3 times larger elements, so this is the sum of 3 to the power dimension elements of the grid. And then we take this sum not over all elements of the grid, but only over those elements for which this 3 times larger set has positive measure. And it turns out that if we assume that if we only count those guys that 3 times larger set has positive measure, then those guys cannot just barely touch the measure. So it turns out that in this version, this definition makes sense, doesn't depend on the grid. This sum, of course, depends on the grid, but up to something sub-exponential, which is going to be killed by the dividing by the level of epsilon. And moreover, this restriction doesn't change the value for Q positive. So it is indeed the same formula, but now written in the way that, okay. So we have 2 things, yes? Local dimension and LQ spectrum, and the result of, well, it was 82 or something like this. Henschel and Procaccia was that actually they are related to each other. That is that one of them is the Legendre transform of the other. And the proof is very simple, because basically what does it mean that how the dimension of the point of the local dimension equals alpha is beta? It means that we have at level epsilon something like epsilon to power minus beta squares in this grid, each of which squares has the measure approximately epsilon to power minus alpha, epsilon to power alpha. So we take this over all possible alphas and we put it into this sum and we see what we get, and what we get is exactly Legendre transform. Okay, so in this case, what we have, well, everywhere the local dimension cannot be smaller than S in our projection, back to example of Solomyak, but we have one point at which the local dimension is strictly smaller, right? Because the measure of the cylinders, measure of the ball is much larger, because there are plenty of cylinders going there. Okay, then LQ spectrum is given by the Legendre transform, and because of this point, for Q large enough, this point is going to dominate everybody else. And for this reason, there will be a drop of the LQ spectrum. And this is the end of the theorem, and this was, no, it was really done more than 40 years ago.
Questions online, maybe?
I have a question.
Yes?
So you said that this remark by Balázs says that for Q large enough, there is the dimension drop for the LQ dimension of the natural measure.
Yes.
But is it clear what happens just with the Hausdorff dimension of the natural measure? Is there also no dimension drop as for the attractor, or is it not clear?
would think that there should be an argument saying that the dimension should be S. Okay, I think it should be, the argument would be basically that for this projected system with overlaps, there will still be a measure of maximal dimension. And if there is a measure of maximal dimension, then the only measure that can be is the measure which had dimension S in the symbolic space, and there is just one such measure. But the starting point, I'm at the moment not completely certain. Why is it true? I believe it is true, but I don't see at the moment why.
Okay, thanks.